Hi everyone, my name is Samuel Liebana and I'm a PhD student working with Armin Lack, Andrew Sachs and Rafal Bogac at the University of Oxford. I'm very happy to be giving this flash talk at this Neuromatch conference 2021. I'll be speaking about my work on designing a learning race model of visually guided mouse behavior for a two alternative choice task being studied in Armin Lack's lab at Oxford. If you have any questions at the end of the presentation, please do not hesitate to contact me. I'd like to start by providing a brief description of the motivation behind this work. Current models of two alternative voice choice behavior are limited in that most capture only static performance after training and do not model change in behavior over learning. Those which do model change in behavior mostly aggregate data from several trials or sessions, losing the temporal resolution needed to accurately study learning dynamics. Some models capturing changes in behavior at the trial level have been proposed, but most are very expensive to train on large datasets. In this paper by Roy et al. From 2021, the authors address most of the above limitations with the sidetrack toolbox for Python. However, their behavioral model was only designed to capture varying choice probabilities and not timing dynamics. Our model builds on the work by Roy et al. By changing the behavioral model from a logistic regression model to a race model, so that with a similar set of assumptions, it can capture varying choice and timing dynamics at the same time. Using JAX, a high-performance numerical computing library for Python, and the Bayesian fitting framework from Roy et al., we were able to fit the model to data from subjects with several thousands of trials in a matter of minutes. The Bayesian fitting framework used also makes it very easy to include parameter learning rules, which can tell us something about how the subjects are learning to optimize their choices and timings. This new model also allows us to study the reward rate on a trial-by-trial basis, a variable which is known to be important for learning. The experiment being conducted in Armin Lack's lab at Oxford consists of a simple two alternative choice task where water-deprived mice have to choose between rotating a wheel left or right, depending on the position of a grating with varying contrast levels across trials. This is also known as the IBL or International Brain Laboratory Task. Correct choices are rewarded with water and incorrect choices punished with a timeout. With 50% probability after each high contrast and rewarded trial, the mice may enter a debiasing routine where they are presented repeatedly with the same stimulus until they get it correct. The model arose as a necessity to study the learning dynamics of mice learning how to perform this task. Here, the left-hand side shows a closer view of the experimental setup and the regions in striatum from which we recorded dopamine release throughout the experiment. On the right-hand side, you can see a schematic of the model architecture. The race model has two independent processing pathways, which accumulate evidence in favor of left or right choices through integrators, which race each other to a threshold. The first to arrive determines the choice made by the model. The model receives as an input a noisy estimate of the contrast level of either left or right stimuli on each trial. This input is multiplied by a perceptual weight for each pathway, WL and WR. And to this, a left or right action weight, BL and BR, and some Gaussian noise is added to give the value which is accumulated in the integrators over time. A typical trial for the model can look like this, where the two integrator traces race to the threshold, and the first to reach determines the choice and the reaction time. The parameters which are learned on a trial-by-trial basis are the perceptual and action weights and the decision threshold. The variances of the input and integrator noise instead are assumed to remain constant through learning. To constrain the variability of the parameters from trial to trial, we use the same method as Roy et al. And impose a Gaussian walk prior on parameter updates with a variance for each parameter, which are set by maximizing the model evidence with the empirical Bayes algorithm. We allow for high variances at session boundaries to capture additional learning or forgetting that may occur in between sessions, but within a session, the variances remain constant. An example of the parameter trajectory over trials learned by the model for a mouse is shown here. We observe a general trend whereby the perceptual weights increase over learning and the action weights oscillate with a smaller magnitude. The threshold remains constant for the most part. From these fits for each mouse, we can calculate the psychometric curves at each trial. If we split all the trials for each mouse into quartiles and average the psychometric curves across the trials in each quartile, across all mice, we see a good agreement between the original metrics calculated purely from behavior and those predicted by the model. Here, the gray lines indicate individual mice, and the black lines are the averages across mice. The same agreement is observed between the reaction time versus contrast curves over quartiles for the original behavior in the model. Having set up a working model which can capture choice and timing dynamics on a trial-by-trial level, we are now considering changing the prior so that it further constrains the parameter updates with a learning rule. This would allow us to test different such rules to investigate which principle may be guiding learning. After fitting the model for all mice, we noticed that mice could be categorized by their learning trajectories, indicating that different mice may be adopting different strategies to learn the task. This is something we would like to investigate in more detail. Lastly, we are currently focusing on finding neural correlates of the different parameters and variables that the model allows us to define. To discover the functional role of dopamine across the striatum is our goal. I'd like to finish off by thanking my supervisors and the team at Armin Lack's lab who have made this study possible.